total would triple. It would triple.
Yeah, capital was 3 originally.
I mean, no, sorry.
You were 3
That'd
for
be
capital
third.
last time. And then you changed it to 2 for third.
Oh, thank you.
Sorry, not triple. It would be a third of what it was.
Yeah, based upon this right here, we have basically from the plates over kappa. So this is 1/3 of what we started with.
Would your voltage be 2/3 of what it was before?
I was thinking 3.
Uh,
3/2.
3/2.
Yeah.
Yeah, because we now have kappa is equal to 3. Going from this step to this step, we're not changing anything here other than we're changing kappa. And so it's 3 times what this was, so this is 3/2 C sub 0. And last, the voltage.
It would stay the same. Yeah. Would it stay the same?
They would not actually stay the same.
No, it would not.
Because the voltage depends on, we have voltage in 2 equations, here and here.
Bless you. Okay.
Whichever way you go about it, you should get the same answer. If you don't, then either you've made a mistake or, as I did one particular semester, I gave too much information.
Would it be 2/3?
Yes.
Yeah.
All right, so from this equation up here, we have the capacitance, which is 3/2 C sub 0, is equal to Q, which is the original Q naught over delta V. Delta V would therefore be Q naught over 3/2 C naught, which is 2/3 Q naught over C naught, which is 2/3 our original voltage. Looking at the bottom equation down there, delta V is equal to the total electric field, which is 1/3 E sub naught, times the distance, which is twice what it originally was, 2 D sub 0. So you get 2/3 E sub naught D sub naught, which is back there again. All right, questions to hear, because we're about to reconnect the battery. People are copying some of that stuff down, so then reconnect battery. That's the word battery there, I guess with a little bit extra flourish on the Y. I'm assuming people have this down. But it's going to be immortalized until the electromagnetic pulse comes through and destroys everything on YouTube. All right, so when we reconnect the battery, what happens?
Will voltage now stay the same?
Say the same as, I mean, still 2/3?
Yeah. I'm not sure if that logic makes sense, but
We go back to what Janice was originally saying. Once we reconnect this 20-volt battery, then
Everything goes back to the original.
yeah, voltage has to go back to the original. Anything going to stay the same? Does reconnecting the battery change? What does reconnecting the battery change in terms of? Well, we can start at the top, capacitance.
What does K say? Does kappa stay 3?
Yeah, we haven't changed any of this stuff right here. It's still, we still have a dielectric in between, and the distance is still doubled.
then it doesn't change.
Right. Because the configuration, capacitance is based upon the configuration the physical nature of it, and the physical nature of it did not change from that previous step to this step. And so this is still 3 halves C sub 0. So we now can find Q sub naught.
It would stay the same.
Because
You wouldn't
C
be
is
charging,
straight.
I mean,
All right,
it's not,
one of you.
sorry, it's no longer gonna be fixed because the voltage is reconnected, right?
Right, charge has someplace to go.
Reconnected.
Yeah, so charge is not fixed. And Sarah, you were saying specifically?
It was gotta be different because, like, C had changed, but V hadn't, so Q had to change.
Yeah. And so from here, Q is equal to C delta V. And so if we just multiply those together, this has to be 3 halves of Q sub naught. And now so charge has changed. What else, therefore, what else will change?
Signals.
Make sure I didn't flip something around there. So Q is C delta V, I'm good with that. And there's C, there's delta V. Yeah, I'm good, all right.
2/3.
So sigma is that,
Sigma is what changes.
okay. So 3 halves.
Oh, 3 halves.
Oh, man, my
Oh,
mind
no,
is
yeah,
just
sorry,
elsewhere right
yeah,
now.
yeah.
I'm assuming you said 3 halves.
I did.
The area doesn't change. Q does, is now 1.5 times what it used to be. If we think about it, when we went from this previous step to this step, we increased the voltage between the plates. When you increase the voltage, that actually is going to put more charge on the plates. All right, so now that the charge density, surface charge density has increased.
So the electric
They're
field.
both of the E's. Yeah.
Okay, so what is, this is probably the easier of the two.
3 halves.
So that's 3 halves. What we started with?
And then 1/2 E. Something like that.
And so we should be able to get that from 2 different directions and get the same thing. So this should be the voltage divided by the distance. So that divided by twice the original distance. So this is 2 D sub naught, just as a visual reminder. And then also it should be basically the electric field from the plates divided by kappa. But sigma increase, so it's that divided by, 3, so 1/2. Hopefully you can see the potential here for a test question. So there's a number of test questions where I go through this scenario and you're supposed to, there's, at some point, sometimes I go, what is the actual value, what are the values as you change, and there's other ones where I say, assume these are initial values, just tell me what it is in terms of the initial value, basically like this. I mean, you have the initial values over there, so you can just multiply times whatever to get what you need. Although when I did it this way, because I thought this would be just a lot easier, so people don't have to go through and do all the calculator stuff. But some students still went through and did the numbers for every single one of these. And then I got to the point where I just needed something different. And I said, all right, so let's fix 2 of these things and change 3 of them. And just leave it open-ended. How could you go about, in this particular case, keeping voltage the same but changing everything else? Well, that did it. Now, that's not a particularly exciting problem, if I said that, but then I got to, the first time I did it, I was really excited because it was a new kind of problem. And I said, how can you keep these 2 things fixed but change these, double these 2 values, or something along those lines? And I came up with something that was impossible, because careless error on my part. And so the next year, I then added in the, if it's not possible, show why, just to cover myself. So that's the evolution. So when you're looking at the test, if you look, you might see an evolution of those type problems. All right. So you can pretty much what I'm heading towards is that on test one, your first test, there's gonna be some problem dealing with manipulation of the parallel plate capacitor. And there should be one on the master set too. If not, there should be. Questions before I erase this and we do sort of the last topic from chapter 19. And we should be able to finish that to the point where we can talk about when the first test is. And I know you're all excited by that.
Yes.
Because right now, all of you have a F on your test average, and so all of your grades are probably at best a D or something like that, so. Actually, I haven't recorded the lab grade yet. I finished grading the first lab, I haven't recorded yet, so you have an F on your lab average too. And, did I have the quiz back?
Me and Katie worked out.
But, okay, I think that also, I have it graded, but I haven't recorded it yet, so all of you are failing at the moment, so let's see if we can improve that.
Like an hour, 45 minutes away. Hiking. And I was like,
Just you and her.
no, me, her, and her family.
All right.
Oh, yeah.
Classic battery hooked to the capacitor.
Yeah.
All right, so I have a battery and a capacitor, as we have done several times before. We basically charge up this to some value Q. This has some capacitance C. Now I'm going to change the scenario slightly. I'm going to keep my battery there, except this time when I connect it to the plates, I'm going to split the wire to touch the plate in two spots. What effect will that have on any of the quantities we had just listed? By now having two wires touching the plate instead of one. Your gut feeling, what is that going to do?
Nothing.
Yeah. Because as the electrons come in, before they had only one path to take, now the electrons get to a certain point and now they can go this way or that way. Or if you're not observing, both ways. So now what I'm going to do is I'm going to take this capacitor here, and I got the split right there, except this time I'm going to put a incredibly tiny little slit through the two plates. I should just draw them as one and then erase a line. And then I'm just putting a small little cut there so I've separated the plates. Assume that any cut that I made in the plate does not actually change the size of the plates, the total size. They're now just half. I have two that are half the size that they started with. What's now affected?
Capacitors.
How? What's your gut tell you?
My gut tells me that since they're still getting the same amount of voltage and they're like still the same size and everything, that the charge is gonna stay the same.
Total charge.
Total charge is gonna stay the same.
Okay.
But now that there's, in essence, two capacitors just getting the same thing, somehow the capacitance is going to change. I don't know how.
Okay. So in terms of, let's just talk about in terms of charge. In terms of charge, let's say that this holds 100 units of charge, and this is negative 100 units of charge. If I cut the plates in half, how much charge do you think is on each plate?
50.
Yeah. So, go back to C equals Q over delta V. What's the voltage across each plate? Oh, I didn't tell you. Let's go with the 12-volt battery again. So, if I got a 12-volt battery here, what's the potential drop across this one?
12.
This one,
12.
this one,
12.
and this one?
12.
Yeah. Because again, no matter what path you take, if I gain 12 here, I'm going to lose 12 going across that path or that path. So my voltage stays the same. My charge has been cut in half. So what's the capacitance of each of these?
It would be half of what it was.
Yeah. So if this is C here and that's C there, this would be 1/2 of C and 1/2 of C. What this is showing is I did it sort of backwards, but adding capacitors in parallel equivalent capacitance, so C EQ, this is equivalent capacitance. Equals just the sum of the capacitors. So let's define what parallel is. She's not the instructor you're looking for. So in parallel, common start and end with nothing else in between. Same voltage. If they are in parallel, then when you at some point you're going to come to a junction and you have a choice of going across one of them or you're going across the other one. So if I've got, or for three of them, you have a choice of three. These are a parallel capacitor because I have a common start and end. So one of them is the start, one of them is the end. And when I get here, they will have the same voltage going across each because as I go from here to here, no matter which path I take, it's the same voltage because I have the same start and end. And I don't have anything in between. Now, when I said something in between, what I mean by that is I got my same start here. Let's just have two right like that. They have the same start and end, so that's good, except the voltage across this capacitor is not the same across this one or this one. Those cannot be in parallel because I got something else in between. So not in parallel. And I gotta be careful with the wording there. Instead of saying not in parallel, no two capacitors are in parallel. You could comment that this one is in parallel with this series, but it's not in parallel with either of them individually. So, equivalent parallel is just the sum of the individual capacitors. So just a quick and dirty example. Let's go to this one over here. This is 3 farads, 4 farads, and 2 farads. Come up with a fake scenario. You're designing a piece of equipment and you have 3 different capacitors right here, but suddenly there's a shortage of capacitors, so you need to take these 3 out to use them for another piece of equipment, and you need to replace those capacitors with a single capacitor. What is the single capacitor that can be used to replace those 3? or what is the capacitance of a single capacitor that could replace all three of those? If I pull those three out and put in just a single one.
9 farads.
Yep. It's as simple as that. Questions before we talk about things in series? Draw a scenario here. That'll be 12 volts. All right, I left some big space there because I want to draw some stuff in the middle. So I now have a battery hooked up to another capacitor with a large distance between them. This would have a small capacitance. If this were physically, if I actually separated them that far, and that's the lab you're doing in however many weeks. All right, so let's think about what happens with the capacitor. Once I have it hooked up here, I have an electron leaves the negative side, it cruises around, the electron shows up over here, chasing an electron off of that, leaving a positive line. Well, actually the positive stayed there, but leaving it positively charged. Then I put another electron here, and the other one goes off like that, another electron here, and so on. Then we build up a whole bunch of negative charges on one side, positive charges on the, and left with positive charges on the other side. That's a very quick slurred version of what we did at some point last week. Now I'm going to change the scenario. Still 12-volt battery. This time, I'm going to add a metal plate in between. Some metal. So an electron comes along here, gets onto this plate. Now what's going to happen?
Trace an electron
Chase an electron off.
the metal plate.
Oh, so the electron's going to jump across the gap?
Yeah.
Assume that don't have so much voltage that we're going to spark. So it's not going to go off the plate. However, if it's not going off the plate, what's happening to that electron?
It's going to the other side.
Yeah. So we get an electron over here, and this is the positive side over here. When the electron shows up over here, what happens on this plate?
The electron would go out, so leaving a positive charge.
Yeah. So in essence, putting the metal plate in between, all we're doing is we're still chasing electrons around. Ultimately, we're still storing just as much charge as we did before. Now, this right here, we have this metal plate. Now I can make it look a little bit fancier here, so let's do that. So instead of having the solid metal plate, I'm going to save some material here. I still got my outer plates right here, but the middle plate, let's make sure it's connected to the battery. The middle plate, I'm just going to take into two thin plates, and I'm connected by a wire. So the metal plate transforms. So I'm putting charge on this side, I'm chasing charge away from that. Nothing has changed from the previous scenario other than instead of them, they're still on the surfaces, other than when they move from one surface to the other, they have to go across this wire. Instead of just traveling however they want from one side to the other, now they have to go across a wire. Physically, it probably takes just slightly more time. So instead of taking 1 microsecond to charge up, it might take 1.1 microseconds to charge up. But I still have 4, 5, 1, 2, 3, 4, 5. But these are capacitors too. So what I want to know is if I went from here to here, in other words, if I have them in series, and what I mean in series is that if I go across one and I continue in that path, I have to go across the other. There's no junction in between. So let's go ahead and define that one. Capacitors in series. Two capacitors, or two or more capacitors with no junction in between. Two capacitors connected. I didn't want you to think if I just took two capacitors and set them on the table that they're in series. There has to be some connection between the two. So there's no junction in between here. There's no place for any electron to take a different path. I know that the equivalent capacitance is going to be equal to the charge over the voltage. I have, we'll call this C1 and C2. Let's call this, I'm going to put a little sub t down here for this being delta V sub t for total, t for total. I know that delta V total has to be equal to, if I'm gaining 12 volts here, I have to lose 12 volts going across these two. I can't lose 12 across one and then nothing across the other. It can't be 12 across both. It has, but the sum of the voltage across here and across here, the sum has to be 12 volts. So this would be the voltage across one plus the voltage across two. This would be the total charge over the equivalent capacitance is equal to the charge across one over the capacitance of one plus the charge across two over the capacitance of two. And hopefully, as I have sketched out here, the charge across the two plates here is the same as across these two plates, across these two plates. Q is the same. So this becomes 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus however many you have in series. So 1 over the equivalent capacitance in series is the sum of 1 over the individual ones. Questions to hear? Benjamin.
What's the difference between those two pictures? The
Between-
one and the right one?
Do this one and that one? Here I just put a solid metal plate here. And in this one, instead of having a solid metal plate, I broke it into two thin plates with a wire connecting them. Other questions?
Why is Q1?
Why Q1?
Yeah, and then why is it equal to
So I added an extra step here. I know that capacitance is charge divided by voltage. So voltage is charge divided by capacitance. And so I was just saying that the charge on capacitor 1, I just called that Q1. So the voltage across this is whatever charge is on capacitor 1 divided by the capacitance of 1.
Okay.
And the charge across 2 is over the capacitance of 2.
Yeah.
But what I started out with was trying to show that the charge is actually the same. The charge on 2 is the exact same charge on 1, which is the exact same charge over the whole thing.
Oh, so you just put it as 1 just to make it easier.
And so, and then going from here to here, since the total charge is equal to Q1, which equals Q2, we divided by, equal to Q. We just divided by Q. Or other questions? All right, same fake scenario. You have a shortage of individual capacitances. You need this 2, 3, and 4 farad capacitor for other devices, and you have a stockpile where you can take one out. I'm going to take these 3 capacitors out and replace it with a single capacitor. What is the equivalent capacitance of these 3?
Nine farads.
Say it again?
9 farads.
No. Because they are in series. Because when I go across, if I go across this one, there's no junction in between. There's no path for me to go elsewhere. I'm going across that, going across that. So these are in series.
Is it 1 over 9?
Pardon?
Is it 1 over 9?
It is not 1 over 9.
So it'd just be 1/2.
If you can do it in your head, more power to you. I would recommend a calculator. It could be done in your head, but I
That's
guess
a
common
challenge.
denominator, 12.
That's a challenge. Yeah, it's 12.
So we got 6 plus 4 plus 3, which is 13.
13, 12. Oh, no. 13. Sorry. Wait, isn't it 13 12? You said the common denominator was 12, right?
I did say the common denominator was 12. Let's work through the math, considering there was such a lack of people just shouting out. We'll do it here. 1 over the equivalent capacitance is 1 over 2 plus 1 over 3 plus 1 over 4. If I add the fractions together, I get 13/12, unless I made a